Hello, everyone. Welcome back to another lesson on pressure. For part four, we're going to talk about atmospheric pressure. Now, before we talk about atmospheric pressure, we need to talk about the atmosphere. What is the atmosphere? Now, the atmosphere is a layer of air that covers the earth. And the atmosphere is basically the air on Earth, and it's made up of all of the gases that we can find on Earth. So, oxygen, carbon dioxide, water vapor, nitrogen, and etc. The atmosphere extends up to 1,000 kilometers above the surface, and beyond that is the outer space. Airplanes usually fly at about 10 kilometers above us. All of the gases in the atmosphere totals up to a mass of 4.5 times 10 to the power of 18 kilograms. So that's 45 with 17 zeros behind it. So that's quite a big number. So that's quite heavy. So in other words, the atmosphere is quite heavy if you calculate its total mass. Since the atmosphere has mass, that means it has weight. So it's quite heavy, so it can cause a force that is weight on us. The weight of the atmosphere exerts a pressure on anything on the surface of the earth. So you can see from this picture here, when you are inside the atmosphere, the weight of the atmosphere is exerting pressure on your body. So it's like having a 1 ton of mass on top of you. At sea level, the atmospheric pressure is about 1.1 times 10 to the power of 5 Pascal. So that's 1 with 5 zeros behind it. So it's 100,000 Pascal, or 1 times 10 to the power of 5 newtons per meter squared. That's a typo there. This number here is also called 1 atmosphere or 1 ATM. So just in case you don't know, sea level is basically the level of the ground that is the same level as the sea. But strangely, even though there's this weight of air on top of us pushing down on us, exerting pressure on us, we don't feel it, right? So why we don't feel this pressure? This is because of two reasons. First reason, the pressure inside our body is almost equal to the atmospheric pressure outside of our body. So the pressure that is being exerted by the atmosphere on the outside is being cancelled out by the pressure inside our body. And this is pressure from the air inside our body, the blood inside our body, and they equal out. So we don't really feel the atmospheric pressure. The other thing that you need to know is that the air exerts pressure in all directions. So the pressure doesn't just come from on top of you, even though the pressure comes from the air on top of you. This pressure is also exerted around the body because the air surrounds your body when you are in the atmosphere. So it's all around you. It also pushes up and balances out the pressure on our bodies so that we don't collapse. Now, when you are calculating liquid pressure, you need to also consider the atmospheric pressure. So you remember this example here. This is example 4. We calculated the liquid pressure. And in order to calculate liquid pressure, we use this formula, pressure is equal to rho GH. And we said that the pressure at the surface of the liquid is 0 because it has 0 depth. It is like this because there is no atmosphere above the liquid. So if you study this diagram carefully, I wrote down here that on top of the liquid, there's no atmosphere, there's no air, it's just vacuum. So that's why the pressure is 0. But if you expose the surface of the liquid to the atmosphere, to air, like in this picture here, then the atmosphere gives pressure at the surface of the liquid. So, however, if there is air above the liquid column, then we need to consider the effects of atmospheric pressure. So now the pressure at the surface is not 0, it is 100,000 Pascal, or 1 times 10 to the power of 5 Pascal. So when we are calculating liquid pressure, we need to add the atmospheric pressure to the equation. So it's just the liquid pressure equation plus the atmospheric pressure if the liquid is exposed to air. Let's do this example, and we can see this in example 6. A block of wood is pushed into the water. What is the liquid pressure on top of the block of wood? So what's the liquid pressure here? Okay, so because this water, this liquid is exposed to air, we need to think about the atmospheric pressure that is also pushing down in the liquid. So we have liquid pressure pushing on the wood and atmospheric pressure also pushing on the wood. So we use pressure is equal to rho GH plus the atmospheric pressure. Rho is the density of water, and the density of water is 1000 kilograms per meter cube. G is 10, the height is 1, and the atmospheric pressure is actually, in this case, we're going to take the atmospheric pressure at sea level, and that's equal to 1 times 10 to the power of 5. So that's basically 100,000 Pascal. So that's equal to 10,000 plus 100,000. So overall, it will be equal to 110,000 Pascal, and that's the answer. What about at the bottom of the block? So B is the same formula. Rho is 100, the density is 100. G is 10, the height or the depth is 1.5, and the atmospheric pressure, we still take it as the pressure at sea level. And 1000 times 10 times 1.5, that will give us 15,000 plus 100,000, and at the end, we will get 115,000 Pascal. Okay? So just bear in mind, just be careful when you are calculating liquid pressure. You have to check whether it is exposed to air. If it is, then basically you have to add the atmospheric pressure. So how does atmospheric pressure affect us in daily life? Here are some important examples. Number one is suction cups. Okay, so I'll basically explain to you how these things work and how these things can stick onto walls. When you push a suction cup onto a surface, you are pushing air out from the space beneath the cup and the surface. So let's use this as an example. So this is a very simple form of a suction cup, and these are the air molecules. So let's just ignore them for the time being. And there are air molecules inside the cup. And when you push this into the wall, what's gonna happen is that the cup will bend like this, right? And then it will push the air molecules from inside of the cup. And then when you stop pushing, the cup returns back to its original shape. But this time, there's no air inside of the cup. So you then create a space inside the suction cup, which has no or less air. And at this point of time, there is more air outside of the cup, so air pressure is higher outside than inside. So you see these air particles here. They are pushing the cup, okay, because they have pressure. They are pushing towards the cup and exerting pressure on the cup. And because there is nothing inside of the cup, so there's nothing pushing back from inside of the cup. So the air pressure outside pushes against the cup, and this causes the cup unable to move, so the suction cup sticks to the surface. So that's basically how it works, right? Now, something for you to think about, why does a suction cup only work on smooth surfaces like glass and not on rough surfaces like rocks and wood? So it's time to think about how the air molecules behave when the suction cup is pressing against a rough surfaces like rocks and wood. Another example where atmospheric pressure plays an important role in our life is when we are drinking straws. So when we drink through a straw, we suck air out of the straw. So here, before there are air particles inside the straw, but when we suck, there is no air particles there, or there's less air particles there, so there's less pressure inside the straw, right? So there's less or no air inside the straw, the pressure inside the straw is lower. And then because the pressure here is lower, the atmospheric pressure, on the other hand, is always pushing on the surface of the liquid. So this atmospheric pressure here pushes the liquid down. And you can imagine that causes the liquid to go into the straw and up into our mouth. So the next point here, since the atmospheric pressure is greater, it pushes onto the surface of the liquid, forcing the liquid to rise up the straw and into our mouth. Now think, can you drink through a straw without atmospheric pressure? For example, like in a vacuum. So if you are out in space and there's no atmosphere around you, there's no air around you, can you drink from the straw? So I want you to think to figure that out. Now, atmospheric pressure can change depending on where you are. So, as I told you before, the normal atmospheric pressure, that is the pressure at sea level, is 1 times 10 to the power of 5. And so that's basically equal to 100,000 Pascal. And this is the pressure at the sea level. As we go higher, for example, if you go up the mountain, the atmospheric pressure decreases. This is because there is less air available at high altitudes, so there's less air pushing on you, so the pressure is lower. You can see it from this example here. So on the right, we have the picture of the landscape, and on the left, we have the number of air molecules. So if you go higher, you can see the air molecules are getting less and less, and the pressure, the atmospheric pressure, also decreases. So if you go out to outer space, there's no gas there, there's no air, so there's no atmospheric pressure at all. But if you go nearer to the ground, there is more air and there's more atmospheric pressure. So atmospheric pressure depends on the altitude or the height. So again, why does this happen? When you are at the sea level or at the ground, you have a longer column of air on top of you, so you have more air on top of you. Therefore, all of that air pushing down on you, and it causes a large amount of atmospheric pressure. But if you are higher up on a mountain, you have a shorter column of air, you have less air on top of you, so there's less weight and less pressure being exerted on you. Because of this, it has an effect to our body. We live normally under normal atmospheric pressure, which is at sea level, and this is because our body has a fixed internal pressure, which is at the same pressure. The pressure inside our body and the pressure of the atmosphere at sea level are basically the same. But if there are changes to our surrounding pressure, if the atmospheric pressure is different, our body can sense this, and the pressure difference can have an effect to our body. So if you go to higher altitudes, the pressure outside can be lower than our body pressure, and this difference in pressure can cause nose bleeding. You can also feel this when you are in airplanes. If you fly at high altitudes where the air pressure is low, you can feel something is going on with your ear. Your ear, in Brunei, we say your ear feels bangal, and this is because of the change in pressure. So in order to make passengers safe and comfortable, the cabins are pressurized to normal atmospheric pressure. So that is inside airplanes. Okay, so the effects of the difference in pressure in our body, there are two that are well known. The first one here, when you are going up to higher altitudes, like in airplanes or mountain climbing, we sometimes feel that our ear is blocked. This is caused by the difference in pressure, and we call this in Brunei bangal, okay, telinga bangal. If we dive underwater, the deeper we go, the pressure increases. So if you remember, liquid pressure depends on the depth. The deeper you go, the more pressure it is. And then if the pressure gets too large, it can overcome the pressure inside our body and crush us. Yes, so if you dive too deep inside of the water pressure can crush you and can kill you. So that's it about atmospheric pressure. Just know that atmospheric pressure at sea level is 1 times 10 to the power of 5 Pascal or 100,000 Pascal. And make sure you know that atmospheric pressure changes with altitude. So the higher you go, the less atmospheric pressure. And if you are at sea level, that is where the atmospheric pressure is at maximum on Earth. And then you have to consider atmospheric pressure in calculations to determine the total pressure of a point in a liquid. So that means when you are calculating liquid pressure, which is P is equal to rho GH, if the liquid is exposed to air or the atmosphere, then you have to add the atmospheric pressure to the formula in order for you to calculate the total and correct pressure exerted in that liquid. In the next part, we're going to talk about a device that's called a barometer.